Okay, let's do a short historical review of motion. And we're going to start with the ancient Greeks and a guy by the name of Aristotle who lived in around 300 BC. And the ancient Greeks thought that there was the motion of the heavens and then there was the motion of things on earth. So when it came to celestial motions, the motions of the planets and the stars, they thought that those motions were perfect. And so, for example, they thought that all the planets went around the earth in perfect circles. Okay, then when it came to terrestrial motion, motion of things on the earth, they thought that things were unstable and imperfect. And so they divided terrestrial motion up into, is it up and down motion or is it sideways motion? So their up and down motion idea was that they thought that things tried to get back to where it came from. So if you had a rock and you let go of it, the rock would return to the earth because that's where you find rocks. Okay, if you breathe out, you notice that the air in your lungs goes into the air around you and it kind of just stays there. Okay, that's because air is trying to get back to air. When it rains, water falls to the earth because it's trying to get into a river and then empty into the oceans from where it came from. But when you light a match, a flame goes up. So what would cause a flame to go up? So they imagined that the earth was surrounded by a celestial sphere. And then that celestial sphere had holes in it. Now, outside the realm of the celestial sphere was going to be the realm of fire. So that you'd have fire out here, and then at night, when you would look up into the sky, you'd look through the holes and you would see the fire, and then that's what the stars were. So this also explains, like, when you light a match, the flame goes up because it's actually trying to get back out to here from where it came from. Okay, so this is one of the ideas that they came up with. That's wrong, just in case you're wondering. Okay, then they also tried to explain sideways motion. And so sideways motion, they said that an object, a force, was necessary in order to keep an object moving. Now, in a way, this was pretty close to what's really correct. It's just it's absolutely backwards. So they would say that if you take an object and you want to throw it, that's going to require a force. But they also said that when it's traveling through the air, there still must be something pushing on it in order to keep it moving through the air. Now later during the Middle Ages, they had to come up with an explanation for this, and they said that as an object goes through the air, it parts the air in front of it. Well, that air has to go somewhere. So that air that's being parted as this thing goes through it goes around it, and then it comes out the back. And it squeezes, the air is squeezing on the back of this object, and that's what's keeping it moving forward. Wasn't a very good idea, but it was the best that they could come up with back then. So along comes a guy by the name of Galileo. So Galileo is going to be born at the end of the Middle Ages and at the beginning of the Renaissance. And so he's born in the 1500s. And so he came up with a lot of ideas, and so one of them is what is inertia? So today we talk about what is the mass of an object in kilograms. So another name for mass is the inertia of an object. So it's a property of an object that makes it hard to get moving and hard to stop moving once it is moving. So imagine that you've got a bowling ball and you've got a ping pong ball. Okay, now take the little ping pong ball and put it on the table and then notice how easy it is to get it moving and how easy it is to stop it from moving once it is moving. Okay, that's because it doesn't have much inertia. It doesn't have much mass. Now take the bowling ball. So the bowling ball is going to have more mass to it, something like 1,000 times more mass than what that ping pong ball is going to have. All right, now try to get that bowling ball to move, and you notice it's pretty difficult to get that thing to move. And then once it is rolling, try to stop it with your hand, and you'll notice it's kind of difficult. So that the more mass an object has, the harder it's going to be to get it to move, and then once it is moving, the harder it's going to be to stop it from moving. So Galileo called this concept inertia, and so in Italian it means lazy. So something with a lot of inertia doesn't want to be moved. It's lazy. Okay, so here are some typical masses of objects in kilograms. Another experiment that Galileo did was with the famous Leaning Tower of Pisa thing. So prior to Galileo, they thought that if you had a light object and a heavy object and you would drop them, the heavy object would be faster than the light object because of its mass. So they said that the more massive the object, the faster it's going to fall. And so Galileo, what he did was he took a big heavy cannonball and then a less heavy ball up to the top of the Leaning Tower of Pisa and dropped them, and lo and behold, they both hit the ground at the same time. So they were both accelerated the same amount. And so later he went on to do experiments with acceleration, which I'll show you here in just a moment. But the point that he showed was the mass of an object does not determine how much it's going to accelerate in free fall. Later, we're going to find out why that's going to be true. Okay, then he also did experiments with acceleration, in which he had a ramp. And he took a ramp and he attached bells to it. So he put a bell here, and a bell here, and a bell here. And then that way, as the ball was rolling down the ramp, it would hit these bells, and so he could time it. And he timed it with his pulse. So evidently he had a very steady pulse that he was able to do this. So he did experiments measuring the distance that something would fall. He measured the speed that it would have as it went down, and then he also measured the acceleration of it as it went down. So he was one of the first persons to measure accelerations, and he did it with the ramp. One of the things that he noticed was that if you had a ramp and you let the ball go from, let's say, up here, he noticed that it would roll down, and then if he had another ramp on this side over here, it would always, well, it wouldn't go any higher than a horizontal. So whatever height it is over here, that same height over here, he noticed that the ball would never go any higher than that. And if this was a very, very smooth ramp, then he noticed that it went almost exactly up to the same height that you started it at. And he noticed it didn't depend on the angle of the ramp. So he tried with a ramp at this angle here, and he noticed that it went over to here. And what he did, though, was he kept making the ramp get more and more shallow, and he noticed it always went up to the same height over here. And so then he had the idea, well, what if I just let the ball go and it went, and that there was no ramp over here? How far would it go? And he speculated it would go an infinite amount of distance. Another thing that he had the capability of doing was thinking in terms of abstracts. So that, for example, what would happen if I take a cannonball and I roll it on gravel? Well, it comes to a stop. All right, now what would happen if I take the same cannonball but I roll it on a wooden floor? Well, it's going to roll further. What would happen if I take that same cannonball and I roll it on a frozen lake? It's going to go even further. So then he had the idea of thinking, what would happen if there was no friction whatsoever? So going from gravel to wood to ice, I'm reducing the friction. So what would happen if there was no friction? How far would the cannonball go? And so he came up with the idea that it would go forever. Okay? Well, later you have Sir Isaac Newton, and we'll talk about him in our next segment.